Thank you, David, for your introduction. Welcome also from our side to this Rohde & Schwarz webinar, Boost Your Network with 4x4 MIMO. 4x4 MIMO is a famous term in the mobile industry today. There are operators who commercially launched the feature, other regions, other countries are testing the feature, and some are also hesitant. I'm Arndt Sibila, Technology Marketing Manager for Mobile Network Testing.
Hi, my name is Michael Lawrence. I'm Senior Application Engineer also in Mobile Network Testing, and happy to have you all in our webinar.
We want to show you today that there is a big gain potential offered by 4x4 MIMO capable devices. Let's have a look to the structure of this webinar. I will shortly introduce 4x4 MIMO, theory, a little bit of theory. Then the second point, from peak data rates under perfect conditions to network-wide capacity enhancements. Peak data rates are always good for marketing, for attracting end users. What counts for operators is network capacity, and this is the capacity all over the whole network. Services and applications should work in the whole network with good performance and not only in parts of the cells. So Michael will present the test use cases, so how to test 4x4 MIMO, and he will also provide real measurement data. After some conclusions, we are happy to answer your questions in a Q&A session, so please raise your questions as indicated by David. We have always to start with a forecast of the exploding mobile data traffic. Here is the Cisco VNI mobile forecast from 2017. From 7 exabytes per month last year up to 49 exabytes per month in 2021. On the right side, you see the actual Ericsson mobility report, and this shows the quarterly data consumption from 2012 until 2017. And we saw really a big growth in data traffic last year from Q1 2016 to Q1 2017 of 70%. This is huge. So we are not waiting for the data uptake. We are in the middle of this steep increase. It is real. But what is driving this increase in mobile data? And you see on the left side in the green color, it's clearly mobile video. You see that in 2021, that more than 3/4 of the mobile traffic will be video. And mobile network operators need to continuously increase the capacity in their networks to cope with this increasing data demand. Today in LTE, we are used to 2x2 MIMO devices. Each smartphone supports it. 4x4 MIMO needs 4 transmitters on the base station side, and these 4 transmitters transmit 4 different streams using the same air interface resources. You see here the 4 different colors representing the 4 different streams. On the UE side, we need 4 receivers as well to receive these 4 streams. 4x4 MIMO is only possible with 4 uncorrelated paths on the channel. This is called multipath, and we need this multipath richness. And we need a high signal to interference and noise ratio to realize 4x4 MIMO. This is also called rank 4. In my part of the presentation, I will handle the base station and the UE side, and Michael will discuss the channel characteristics and how to measure the channel. If we are using 4 streams instead of 2, we can really double the downlink data rate compared to 2x2 MIMO. And this finally gives us a real throughput gain in the network because we are using the air interface resources more efficiently. 4x4 MIMO, and now a little bit of theory. You see on the left side the base station with its 4 transmitters and the send signal S. And on the right side you see the UE with the 4 receive antennas and the receive signals R. In the middle you see the channel, and there are 16 paths. Each of the transmit antennas have a channel paths towards each of the receive antennas. So 16 paths for 4x4 MIMO. And the task of the receiver is now to calculate the send signal. Therefore, the receiver needs to solve this set of 4 linear equations to express it in mathematical terms here. So where does the receiver get the channel information from to solve these equations? The answer is channel estimation. And the channel estimation is based on the reference signal of 4 base station antennas. All 4 transmit antennas have their own reference signals in the LTE frame structure. Is 4x4 MIMO a new feature? Not at all. It has been standardized by 3GPP in the very first LTE release. That was 3GPP release 8. And this was 2009, so 8 years ago. So that means in these fast times of always new features, always new technologies, 4x4 MIMO is more like a vintage car. But why Rohde & Schwarz is now talking about it today, why we are doing a webinar about 4x4 MIMO? Because nowadays we see significant commercial deployments, and only nowadays. It started end of 2016. But why not earlier? What was blocking the commercialization? Base station investment, first of all, yes, we need a third and a fourth transmitter, power amplifier, antenna, but this was not really critical. The most important blocking point were the smartphones, because we need a third and fourth receiver antenna and a receiver path in the smartphone. And this was really a technology hurdle. Why we could overcome these barriers now? Basically because the pressure increased and we need more capacity in certain regions of the world like North America and Asia. And the requirements were stronger now for 4x4 MIMO, for supporting 4x4 MIMO. In the last years, we could increase the LTE capacity by using more frequency carriers, more spectrum. Carrier aggregation was used for higher data rates. But this is not really sufficient anymore, and we need to use the air interface resources more efficiently, and therefore 4x4 MIMO was more important. And smartphone designers made some progress in antenna design and antenna technologies, so that now 4 receivers are somehow possible in a smartphone form factor, at least for higher bands. So we want to show you now that if 4x4 MIMO is a vintage car, it's more a vintage race car. If UEs were the blocking point for the ecosystem, it's important to talk about it. What 4x4 MIMO devices are existing today? This is an abstract here from the database of the Global Mobile Suppliers Association. And if you filter the database for the feature 4x4 MIMO and for the form factor phone, you will get exactly this list. So the first 2 entries, the Samsung S7s and the Sony Mobile, are in the list since end of 2016 when T-Mobile US launched, first commercially launched here 4x4 MIMO. The others appeared in April 2017. You see here a set of the Samsung Galaxy S8s are mentioned, and they all have an operator-specific hardware and or firmware. You see as well here 2 Huawei P10 Plus in the list. It could be seen as well from the table that the UE categories in the right column, they doesn't say anything about 4x4 MIMO capability. You see categories from Cat6 to Cat14. We have to be aware that 4x4 MIMO is normally only supported in UEs for the higher bands, starting at roughly 1.7 GHz, because of the smaller wavelengths and the smaller antenna sizes. Chipsets are certainly the precondition for 4x4 MIMO, but there are much more devices built on these chipsets. You see here the Snapdragon series and also the HiSilicon chipset. But the really limiting factor is the antenna design, the 4 receive antennas in the smartphones. And Michael will show you, based on real measurements, that there are still a lot of challenges to be solved concerning the smartphones, smartphone antenna design in particular, although the phones are getting bigger and bigger again, which makes it easier for the antenna. Let's talk about peak data rates. We see promotions from operators advertising LTE up to 300 megabit per second and even more. But these are theoretical peak data rates, and they are normally not experienced in running live networks. So I'm more a friend of real network-wide capacity enhancements. And these allow for network-wide good performance for data-consuming applications like video services. And remember, video services are very important today and even more tomorrow and in future. Peak data rates. Although I like analogies to cars, I decided this time for rectangular tubes for transporting something, a fluid for example. So the width of the tube is the bandwidth of the carrier, and the height is the modulation encoding scheme. So one tube here with 20 MHz bandwidth and 64 QAM modulation encoding scheme can carry 75 megabit per second. 2x2 MIMO is represented by 2 tubes on top of each other. So in total, this makes 150 megabit per second for 2x2 MIMO, and this is standard LTE from release 8 onwards. Apart from the color that has changed, the first difference here is that each tube is higher now. So we are using 256 QAM instead of 64. And this means 1/3 more throughput. So a 20 megahertz wide tube can now transport 100 megabit per second. The second difference is we have now 3 tubes adjacent to each other, which represents the 3 carriers. Yeah? So we have carrier aggregation here. In this example, 2 carriers with 20 megahertz bandwidth and 1 carrier with 10 megahertz bandwidth. So 50 megahertz in total. 2x2 MIMO means we have, again, 2 layers of tubes. So and if we sum up the throughput of all 3 carriers using 256 QAM for 2 layers, 2x2 MIMO, you end up with 500 megabit per second peak rate in this example. And we have to say that operators even measured similar peak data rates in this configuration. Of course, they had to take care about an empty network, best position in the cell, and so on and so on. So now we switched on 4x4 MIMO, and in our tube example, this would mean that we add 2 more layers of tubes. And with 4x4 MIMO, we have now 4 different spatial streams using the same air interface resources. This has to be emphasized, the same air interface resources. And this doubles the peak data rate compared to 2x2 MIMO. Our speed meter shows now 1 gigabit per second peak data rate in theory. But please remember the preconditions. We need 4 receive antennas in smartphones on all bands here. Yeah. Sufficient multipath with similar strength and a high signal to noise and interference ratio. So let's include some sense of reality. 4x4 MIMO with more than 2 carriers is not yet supported by the chipsets. So this is really a limitation of chipset, although they support today 4 carrier aggregation with 20 megahertz and 2x2 MIMO. This is important. Second point, 4 receive antennas are only supported for the higher bands in the smartphones due to the antenna sizes, smaller antenna sizes for higher frequencies. So this is a limitation of the antenna design. So this would be enough for peak data rates, a theoretical peak data rate. Let's talk about real-world capacity. I now want to discuss about all possible improvements that are offered by a 4x4 MIMO antenna configuration, which means 4 transmits at the base station side and 4 receive on the UE side. On the left picture, we are at the cell center somehow. So 4x4 MIMO can be used here. We are using 4 streams and they are using, again, the same radio resources. And this improves the data rate close to the base station. If we are moving with the UE further out, we can use 4 transmit rank 2. That means we are using 2 streams now here. We only see 2 colors, green and red. 2 streams. So these 2 streams are transmitted by 2 antennas each. This gives a gain 2. If we are going really to the cell edge, far out, we can still use 4 transmitters, but only rank 1. So we are using just 1 stream now, and this is only 1 color here visible. And we use 4 transmit antennas. This is called transmit diversity. You see here also the transmission mode 2, which is transmit diversity. And this has a big impact on cell edge performance. Last but not least, we see also here multi-user MIMO. Multi-user MIMO is using 2x2 MIMO for 2 users in parallel using the same resources. Multi-user MIMO is not really visible in today's mobile networks, so far, up to now. It appears to be quite complex to find the right pairs of the UEs because they need to have some relation to each other, some decorrelation to each other. So all in all, you see that there is much more improvement in capacity than only 4x4 MIMO in a favorable position. And we try to visualize the complete gain potential in the following graph. The graph shows the throughput versus the coverage, and what you see now in blue is the situation with legacy LTE smartphones, so 2x2 MIMO. In good position, we can use 2 streams, rank 2. And at the cell edge, we can only use 1 stream, and this is rank 1. So 2 transmit, rank 1. Now you see what comes on top if we have 4 transmitters at the base station and 4 receivers on the UE side. On the left, you see a very high throughput close to the base station. This is exactly our 4x4 MIMO gain. So 4 transmitters, rank 4, 4 different streams. Rank 3, of course, is part of this curve as well. But what is more important is what's happening at the cell edge. LTE networks are normally planned for a stable data connection for 2 transmit rank 1. So the dotted line here shows the typical border of a typical LTE site grid. Exactly here we see a big improvement. So roughly 3 dB we can gain here at the cell edge, and this really helps a lot in data throughput at the cell edge. Of course, we have also the gain in the middle here with 4 transmits rank 2. In summary, we can say that the air interface resources are more efficiently used here, and this translates into capacity enhancements all over the network, not only close to the base station, but all over the network. We already talked about the device, the UE impact, but what is the impact on the base station? We know for 2x2 MIMO LTE networks, today they mostly use cross-polarized antennas. You see on the left side the plus-minus 45 degrees slanted antenna polarizations, the blue and red antenna elements in the picture here. 4x4 MIMO needs uncorrelated antennas. From theory, we would need a spatial separation of more than 10 lambda. And if you look to 1.8 gigahertz here, this is a separation of 1 meter 70. Another possibility is to achieve this decorrelation by a vertical separation. But both methods are somehow unlikely installation options due to mast or site limitations, maybe visual impact, maybe even wind load, and so on. There are so many reasons why this might not be really feasible. For 4x4 MIMO, often what we see here in deployments today is a dual cross-polarized antenna scenario here. Yeah? So 2 antenna columns are close together, roughly 1 lambda away from each other. You may ask now, where's the spatial separation? What is the decorrelation of this antenna? Good question. In fact, the decorrelation is compromised somehow. However, today's antennas provide quite some good isolation figures and also decorrelation figures in their data sheets. In the next slides, I want to talk about antenna examples and challenges for installation. This is an example of an 8-port antenna, and this shows 1 low band and 3 high bands. And we just took antenna examples here from the Katran website just to explain some basics. This is a single column antenna, 30 centimeters wide. And you see here 2 connectors per band. So this would offer us 2 transmit, 2 receive antenna configuration on all 4 supported bands. So this is a straightforward deployment, straightforward installation. Of course, it's important to not mix up the connectors, but this antenna, of course, do not support 4x4 MIMO. Another 8-port antenna example here, 2 low bands, 2 high bands, covering the same band. This is important. So we have a dual column antenna now, 38 centimeters wide in this example. This supplies us 2 connectors per low band, so 2 transmit, 2 receive antenna for the 2 low bands. And we have 4 antenna connectors for the high band. And they are covering the same frequency bands. So this allows for transmit, for receive constellation here in 1 high band. Again, do not mix up the connectors and be careful to use the same feeder lengths, because if you go to 4x4 MIMO, you need to take care about the runtime and the feeder lengths. It's getting more complex now, a 12-port antenna, and this covers 2 low bands, the same frequency range, and 4 high bands, also covering the same frequency range. This would mean we have here now 8 connectors for a high band. So here we have the possibility for a 4x4 MIMO scenario in 2 higher bands. For example, 1900, band 2, and AWS band 4. And we have 4 connectors in the low band. This offers us 2 transmit to receive, so 2x2 MIMO in 2 lower bands. Please remember, smartphones do not support 4 receive antennas in the lower band due to the bigger antenna sizes. And it's definitely clear, the higher the number of antenna ports, the higher is the probability for cabling errors. And they need to be avoided, of course, or at least they need to be tested in field. And here you see 2 examples what can go wrong in cabling. Finally, you may get polarization mismatch. And if you are unlucky, even frequency errors and polarization mismatch in certain scenarios. But you definitely do not gain capacity improvements. For sure, you need test equipment to measure and identify this scenario in field. This concludes my part. I hope I could convince you that 4x4 MIMO is only a part of the possible gain, but the cell edge improvements, they are really what counts for operators. My colleague Michael will show you now some details about how to test 4x4 MIMO and also real field measurements data to support that.
Thank you, Arne, for the nice introduction and the great overview of the theory behind 4x4 MIMO. So I would like to bring you a little bit to the more real field to do the measurements, and what is of course even more important is to have some measurement results. So first of all, I would like to give you a very, very brief overview of tools, what we are offering in our portfolio. So it starts from network scanners, then of course the mobiles itself, and also handheld spectrum analyzers. So we already saw this picture of the H matrix. So we've got the 4 transmitters from the base station side and the 4 receivers in the UE side. So what I would like to emphasize here in this slide is that actually the measurement equipment or the phone has to really to decorrelate the H matrix or to measure the H matrix. There are 2 important measurements. This is first of all the rank, indicating the number of independent layers. And the other measurement is the condition number. The condition number is a measure of how good the MIMO channel will be and how good MIMO will work. So for further ratings, I would like to pinpoint you to an application note which is available on the web already, and there's a new application note coming soon, and you will find it in our internet as well. So let's start with the scanner measurements first. So a network scanner, which is capable to measure LTE, it really measures the channel metrics and then calculates the rank and the condition number for each individual combination of TX, RX. That means from the transmit and the receive path. So measurements are done on the reference signals RSRP, SINR, and RSRQ. So all measurements can be seen in the log file later on. The condition number is important to know as it reflects the quality of the MIMO channel. A low condition number means the channel is well conditioned and MIMO would work very well. In the following graphs you will see these color-coded green. A higher condition number means that MIMO will not work so perfectly, so maybe this channel is not suitable for MIMO at all, and this will be indicated by red colors. The rank, of course, will be a measure from 1, 2, 3, or 4, representing the different special layers. So if you want to do a 4x4 measurement based on scanners, it's important that you have 4 individual RF ports. So you need 4 receivers for that. So if you would see a setup claiming to do measurements which are 4x4 capable, but just using a single receiver, this is not really what we understand about of what we understand of 4x4 MIMO measurements. So this is more 4x1. So 4 transmit, 1 receive path. So in the following graph, so this is a snapshot where we can measure the rank and the condition number. And in the video, which is now just playing, you will see in the waterfall diagram in the upper part the color-coded condition numbers, and you can even hover with the mouse over this graph to see more detailed information about the individual rank, the individual condition number per resource block. In the lower part, you see a huge amount of line charts. So in the bottom, you see the individual measurements for the H matrix, which are just now switched off. So what is remaining here in the blue is the rank, and the red one is the condition number. It's important to understand that the condition number is not linked to the rank. So it could be that the condition number is different for the same rank. The condition number is different for different ranks. Of course, we can also switch between 4x2 and 2x2 measurements. So this is now the measurement for 2x2, even with the same setup. The next view will just show you really that you have to measure all the combinations from the 4TX passes and the 4RX passes. So therefore, actually, you have to look at the sets of always 4. So each individual receive antenna is measuring all 4TX passes. So and here for this waterfall diagram of this subband view, you can understand and learn a lot about your MIMO channel. So if you see like on the left hand side, that you will have some red blocks, so that means in this particular band for this particular received antenna, MIMO is not so good as compared to the others. Of course, beside to the measurements we show, you will also get fundamental information coming from the scanner. First of all, what is displayed here is the rank and the condition number, and of course the T-export, the number of T-exports. The number of T-export is really decoded from the master information block, from the MIPS, because our scanner is capable to decode the master information blocks and all zip messages. Further on, of course, you will see the wideband measurements for RSSI, RSRP, and RSRQ. And in parentheses, you will see the combination of TX and RX antennas, which are used here to show you the highest value for this combination. Of course, the bandwidth is also decoded from the zip messages. Then for sure you can create alphanumeric views, you can customize it by yourself, you can create 2D charts, whatever you like, to just to bring up any correlations what you want to see. There are many more features available in the software called ROMIS, so you can also do scatter plots, X versus Y, and so on and so forth. Of course, there are plenty of predefined charts. So how can we use a scanner to measure a 4x4 installation in the field? So is there any chance to learn something about the installation? So what we can see here in this slide is on the upper right part, we see that the number of T exports is decoded by 4. So that means that this particular cell has 4 transmit antennas deployed or installed. So if we double check this with the subband view, which is on the left hand side, we can see and we can confirm that 4 TXs are working well, and this means rank up to 4 is possible for this cell. So on the right hand side we see again the same picture for the condition number and the rank. So everything is perfect here. This is an example taken in a band 3 scenario. So same setup, doing the measurements at the same location, but now in band 7. Again, we see on the upper right part that the E node B reports it is configured with 4 E node Bs, but our setup can only decode 2 TX antennas. So the black bars, what we can see, are the contribution from the 3rd and 4th antenna. So none of the 4 received antenna can never measure the 3rd or 4th transmit antenna. So therefore also no condition number or rank is possible to be calculated from the scanner later on. So this could be an indication that there might be something wrong in the antenna installation, or that maybe there's a mismatch in the parameterization. So actually this is really where we would recommend that you really go out again, do the measurement, and double check the installation. So beside of the number of detected antennas, which are again circled here with the green box, there's one important feature which is also supported by the scanner, and this is the estimated throughput. So this is circled here with the red one. So that means we can calculate, based on the condition number and on the rank, the estimated throughput per layer. That means per received path, which is very good if you really do an early installation in the field without having really devices available, you can get an indication and start your optimizing the network already. Of course, there are much more measurements important beside the scanner. Now let's go to the UEs. When we are talking about mobile measurements, how can I cross-check how many RX antennas are integrated in my mobile? So there are two important measurements for this. First of all, of course, is the UE capability. This is reported only at the beginning when the UE is registering to the network. So therefore, if you really want to double check this, I would recommend you to put the device in the airplane mode on and off. And then you will see the UE capability, which is shown on the right-hand side. And the green arrows are indicating these layers, which are supporting 4 layers. And the red arrows are indicating the layers which are supporting only 2 layers. So if we just see the enlargement, so for example, in this particular screenshot, band 7 is supported with 4 layers, so this is LTE 2600, and band 20, which is LTE 800, is supported only with 2 layers. As we already learned from Arndt, it is simply due to the fact that it's really not easy to build 4 antennas for the low bands in the small smartphones. Another important measurement to check what is deployed on your side is to look at the RRC connection setup or the connection setup reconfiguration. So here, if you really drill down into these layer 3 messages, you can see here the information of the used antennas, which is circled here with 4 TX antennas and using transmission mode 3. So mobile measurements, of course, are also supported in our software Romis. And this is just to give you a look and feel what you can get. So lots of alphanumeric views, 2D charts, overviews. And this is just to highlight a little bit again that here the rank indicator is really displayed and you have the individual measurements per received pass. So if you're really in a 4x4 scenario, so that means 4 transmit antennas are working, so then you will get up to 4 measurements for the signal level and signer and so on. Another possibility to do measurements in the field is you can use handheld solutions. So this is a Qualipoc based on an Android phone. So that means you will have the special app on your smartphone and you can do very handy measurements here. So and this is just to give you an overview what is available today. So you will see here also the measurement for each individual RX pass, for the RSRP and for the signer, the number of TX antennas. It might be a little bit too tiny here, but there's one thing I just want to explain on this picture already, because we will see in the following slides plenty of these pictures. So we've got the bar charts with the numbers inside, so this is the actual current measurement, and then underneath we've got the line chart, which gives you a little bit the history of the measurement, which is quite important to know and really to understand and to see what was the history of the measurements. So and then of course the actual value is then on the right-hand side of this line chart. Of course, all these views are customizable, so you can refine your own views. You can really just concentrate on the measurements you would like to see, which are most important for you. Of course, on the other hand, plenty of views are predefined, and so it's up to the customer how to use it. So, but of course, now we are most interested in how to really boost the network with 4x4 configuration, or that means 4 TX antennas and 4 received antennas. I have to say it's not an easy job to do this exercise. You have to be aware that if you really want to do this measurement, actually, to be honest with you, you should have 2 similar phones, one just having 2 received antennas and the other having 4 receiving antennas. So this could be done, for example, by different firmware versions. So the older firmware version might not support the 4 antennas, but they are already built into the UE, into the smartphone. So therefore, it's always important to spy into these UI capabilities or in the layer 3 messages, as I showed you before, just to double check this. Then, of course, you have to think about that even more. It depends on the device and on the used chipset. That it could be that 4x4 is supported only for a single carrier. So talking about carrier aggregation scenarios, even if you have 4x4 TX antennas deployed, the UE might not use it because it's going into a carrier aggregation mode and you will see only 2 antennas. But as we already heard, newer mobiles are coming soon, and this is really the future, that we have later phones supporting 4x4 up to 3 bands in the carrier aggregation mode. Okay, so what we see here on this slide, on the left hand side, we've got the results coming from a mobile just reporting 2 RX antennas. And the right hand side, we've got the results coming from another mobile supporting 4 RX antennas. So both mobiles were at the same conditions, so therefore at the same place, so therefore they are in the same radio conditions, so around NEC 80 dBm for the signal level. How to understand the figures? So it might be a little bit too tiny, so therefore I explain to you what is shown in the line charts underneath. Color-coded here, we see the different ranks. Green means rank 1, red means rank 2, yellow means rank 3, and rank 4 was not measured at all. So therefore, it's not present in the picture. So on the left-hand side, we can see, of course, contribution of rank 1 and rank 2. And on the other hand, on the right-hand side, we see a significantly amount of rank 3 on top. So for the last valid value, this is closely to 90%. So if you do a little bit statistic of the job which was done here, so we've got an average rank 2 of 69% and 31 rank 1 for the 2 RX device, so which comes up to an average rank of 1.5. In contrast to that, the 4 RX device shows a rank 3 contribution, average to 53%, rank 2 41, and rank 1 only 6%. So which means, of course, at the end a higher average rank up to 2.5. So here we can see really the boost that already the rank is higher at the same stationary place. So what will be the difference in the throughput? So if we have a look again at the same devices and now having a look at the throughput figure, so we will see that we've got higher data rates for the peak values and also for the average values. So peak data rate 52 versus 96 is a clear evidence for the boost of the network, and of course the average throughput of 27 megabits per second compared to 48 megabits per second, which is a significantly improvement by using the same radio resources in the network. So this is really the evidence, and we proved that 4x4 will really help you to boost the network. So, but as we already said, 4x4 is not always only to put the peak data rate, and I've got a very nice example here that 4x4 can even work at the cell edge. So in this screenshot we can see that the signal level is really representing the cell edge. So we've got something around NEC 110 dBm for the best received pass, and we can see that still a rank 4 is measured up to 40% or even sometimes higher. So this part of the measurement, which is representing the rank 2, was an idle mode measurement, so it was before the FTP session or the HTTP session started. Yeah, so we can ignore this. So on the other hand, we can see that even at the cell edge, we will achieve a peak data rate up to 12 megabits per second, which is tremendous. Of course, why do we measure a 4x4 at the cell edge? Yeah, at the end of the day, the base station takes a decision with its scheduler. So it tells the mobile, the UE, which rank to be used in which transmission mode. Yeah, so and therefore it is a little bit out of control for the person who is doing the test without knowing the holy algorithm of the scheduler to do these tests. So you need a little bit of luck, and of course you should also go into the discussions with your infrastructure supplier to get some more information about this. So, but what we already saw from the previous slide is that we have, of course, different quality of the 4 RX paths. So what we see here actually is already in the line chart, so with the red bars, that we have different values. So, but what is important to achieve a rank 4 or to have a MIMO condition for a mobile? So if we just look at the UE antenna prerequisites, so there are 2 important points. So first, you have to have uncorrelated antennas. So this means actually you have to have a low envelope correlation coefficient, ECC. And on the other hand, the antenna paths, they should be balanced somehow. So that means the received signal level should be in the same order, and there should not be a big difference, because otherwise you will have a big imbalance of the passes, and this will really impact your MIMO performance. So the uncorrelated antennas, the ECC, is definitely something what you have to do in the lab. Yeah, so you have to test in the lab. But to investigate the balanced antenna paths, of course you can do it in the lab, and there are test houses doing this, so measuring TRP, TIS, also using our test equipment like the CMW, the communication mobile tester. But what is really attractive here is you can do this kind of measurement really with our tools. Yeah, so using a smartphone, you have all needed measurements and you simply have to analyze them. So this is what I call simple analysis with drive test tool. So because a Qualipoc or a Romus is classically handled as a drive test tool. So, and what we can see here is actually that there is already a significant offset to be observed from the main antenna RX0 to the fourth antenna, which is labeled or numbered as RX3. So if we just dig into the details, we can see that the differences to the main antenna is starting from 2 dB up to 13 dB, which is tremendous. Some further examples for this. So here we can see additional measurements also taken on the left-hand side for band 2, on the right-hand side for band 4. Yeah. So, and again, what we already saw, the 13 dB for band 2, it was also in the previous slide, band 2. And for the band 4, unbelievable 30 dB. So actually this means for this particular band 4, the fourth antenna is not existing at all. So, and this will have, of course, some impact to the MIMO performance. But what we can see here is we are in perfect radio conditions. So we've got a signal level of next 60 dBm. So taking also the 30 dB offset into account. So that means the fourth antenna still receives next 90 dBm. So therefore, only in this perfect radio conditions, there's the only chance that 4x4 MIMO can work. So if you go further away from the cell, closer to the cell edge, you will immediately drop the fourth antenna pass and switch down to rank 3, 2. That's all. So this is really critical, and this is something what you could really investigate with your measurements. So, of course, you can do this very simple analysis just looking at the line charts and looking at the differences. But there is one more important, more sophisticated way to do the analysis more professional. And this is actually what you can do. So if you plot the RSRP levels of the first antenna, which is the main antenna, versus the second antenna, this is what you see here. So you've got this cloud of tuples. So then, of course, you can add a linear graph, f on x is equal x, because we are expecting a linear behavior of these antenna correlations. then maybe you can add a 5 dB window to this, indicated by the dashed lines. So what we are expecting actually is that all measurement points should be in this corridor of this 5 dB window slide. Then of course it's up to you. If you define 5 dB, you go to 3 dB or 8 dB. Yeah, so this everybody has to decide for its own. So, but now we are talking about thousands of measurements, and of course you always have some outliners in these graphs. So therefore there's a nice trick. Just reduce the transparency of the data points and you will see immediately where's the majority of the measurement points. And here you can see that they are all inside this 5 dB corridor. And last but not least, you will do a simple linear fit with this function f von x equals a multiplied by x. And the increment determines the antenna mismatch. In this example, perfect 0.2 dB. That means these both antennas are really equal to each other. Totally, perfectly balanced. So, what is the result for the third and the fourth antenna? So here we've got a mismatch of 0.6, respectively 1.9 dB. So that means this mobile works perfectly for, or would work perfectly in band 3 for 4x4 MIMO. Another example, same UE, but now doing the measurements in band 7, which is LTE 2600. So let's start with the second antenna compared to the main antenna. So a little bit misleading here. So sometimes the numbering is starting from 0, and here it's called first and second antenna. So here in this graph, first antenna is the main antenna, which is in the other slides named as RX0. However, so the intercept here is just 1.6. It's slightly worse compared to the result what we see in band 3, but still very good. So what about the results for the third and fourth antenna? So here we see a big difference. We see 8 dB for the third and the fourth antenna. So this is again an indication that this mobile, of course, will work with 4 TX ports, with 4 RX ports, so in a 4x4 configuration, but it could be slightly better. So that was a lot of stuff coming from the field. I hope it was not too confusing and you could read a little bit the graphs. However, we will share the slides afterwards with you. We will send a link where you can download then the PDF files. So let's come to the conclusions. In summary, 4 TXs at the base station side and 4 RXs at the UE side clearly boost the capacity throughout the whole network. Challenges you will face, first of all, is at the base station itself. You have to be careful on the installation side. Do not mix up the ports at the antenna. Be careful with the network configuration that everything is correctly done. And there's a big unknown in this game, the scheduler. The radio environment has to be characterized at all. Smartphone impact is also important to know. You have to know the UE capabilities, and also you should double check the antenna performances. Therefore, we can offer you the perfect toolbox, covering non-intrusive scanners like the TSME, TSMA, working together with our software Romus, but also together with the handheld solution QualiPoc, the smartphones, the QualiPoc, which you can also use together with the Romus. Post-processing, quite important in this game, NPA, NQDI, just the keywords here. And last but not least, handheld spectrum analyzer, which were not shown in detail in this presentation, but which are very useful during the installation of the sites. In summary, Rohde & Schwarz Mobile Network Testing, your partner to get more value out of your network.
So this would conclude our presentation today. Thank you very much for watching. Before we come to the Q&A session, we would encourage you to visit our website, mobilenetworktesting.com, if you want to know more. Or if you are interested in more technology topics, please visit our blog. So back to David. Did you get some questions?